it's been a few months where we didn't have the Simon's Quantum Colloquium, mostly because it seemed like everybody was suffering from COVID fatigue and Zoom fatigue, I guess, and so now that everybody has had a chance to be out and about and meet people for a little while, perhaps this is, it's a good time to get back to the colloquium. So I'm very happy to introduce Boaz Barak as our first speaker of this, the renewed colloquium. So Boaz is, I've known him for a very long time. I guess from the time he was just finishing up his PhD, but he's now on the faculty at Harvard. Boaz has done he's done some truly foundational work in cryptography, these non-black box arguments, obfuscation, and in computational complexity. He's the author of a book, the book on computational complexity with Sanjeev Arora, and of late he's started thinking about quantum computing, which is a fantastic thing, and so and today he'll tell us about spoofing strategies for noisy quantum circuits, I believe. So Boaz, really looking forward to this.
Thank you, Umesh, and it really is a pleasure to be here. And if people have questions, it's hard for me to monitor the chat, but so if Umesh, feel free to interject and let me know if there is a question I should answer. And this is based on joint works with Soon-Won Choi, Chining Chu, Shun Gao, Marcin Kalinowski, Misha Lukin, and Kunal Marwaha. So I'll try to take a somewhat unified look in this talk on quantum speedups and unify two views, two lines of work that maybe not often unified in the same talk. So generally, when we are discussing quantum speedups with, say, current devices, we have some kind of a device that someone has constructed, a physical quantum device, which we can think as having some input and some output, and because it's inherently stochastic, so the output, so if the input is theta, or you can think of theta as the configuration for the device or the input of the device, and the output is some string y that is sampled from some probability distribution q of theta. And let's say this string y has n bits, and roughly speaking, we think of this device as requiring something like n resources, constant times n resources for us to execute it or to run it or construct it. And when we talk about speedups, we want to compare with a classical algorithm, and so our comparison is some classical algorithm that has many more resources than the quantum device. And what we want is that basically there should not exist any classical C of comparable resources to the quantum device that gets close to the quantum device. So far this is vague, but to make this more precise, what we really need to do is to come up with some benchmark, right? So we need some benchmark. So this is some function that takes maybe the description of the input and the output distribution and assigns a score to that distribution. And what it means for a quantum speedup, it basically that means that the quantum device gets a value on this benchmark that is higher than the value that any possible classical device can get. So basically the performance on the quantum device on the benchmark should be at least epsilon more than the performance of the best classical algorithm within some resource bound. Say if we're looking at exponential speedup, then within at most to some epsilon n resources on the same benchmark. So far this is very, very abstract, and I think this basically captures any type of benchmark we could think of. I'm not sure if there are questions at this point.
So, yeah, Boaz, I think there was a clarifying question about where the randomness is in the classical circuit.
So let's think of the classical algorithm as also possibly randomized.
So you think there's also additional randomness in addition to theta as input?
Yeah, so you can think of theta as not necessarily random. It can be some configuration, or it could be random, and the classical circuit could also have some additional randomness in it.
Mm-hmm.
So yeah, I mean, okay.
I think that's good. Yeah.
Okay. So let's continue. So ideally, what we would want from this benchmark is we want two properties of it. One property is really, in some sense, crucial, which is statistical efficiency. So this benchmark, in principle, it's a function of a probability distribution. It assigns a score to a probability distribution, and we would like to be able to approximate the benchmark with only a polynomial number, or generally a small number of samples from this probability distribution. If it's a benchmark where, suppose the quantum device, we would need to sample from it an exponential number of times in order to evaluate the benchmark, then that would basically be infeasible. And the second thing is we would like computational efficiency. So we would like this not to be only statistically efficient, but also computationally efficient. And as we'll see, sometimes we can do without the second property, although obviously it's much better if we do have it. And an even better property, which of course many of us care about, but that way, maybe at this point right now it's the cherry on top, is that this benchmark is actually something useful in its own right. There is a reason why you would ever want a device that given theta gets an output that maximizes the benchmark on theta. And in some sense, this third point is also related to the second one. Typically, if you could not even evaluate the benchmark computationally, then maybe that also means that it's probably not very useful, because you don't even know when you got something good. So if there is some reward for producing this output with a large benchmark, then typically that means that you could actually know if the output has large benchmark or not. So let's, we can ignore the usefulness for this talk, although of course it's important. And the the standard example that of a quantum speedup is Shor's algorithm, right? So the factoring problem, you can think of theta as describing a random n-digit integer that is a product of p times q for 2 primes. And the output is a factorization. So the benchmark, basically, given a probability distribution, it just tests if the probability distribution is a factorization of theta. And this is a great benchmark. It's widely believed that classical algorithms will, so quantum algorithms can achieve essentially a value of 0.99 in this benchmark, with a very high probability, will output a factorization. It's widely believed that all classical algorithms can only achieve negligible probability on this benchmark. You only need one sample from the benchmark, or constant number of samples to evaluate it, and you can check factor efficiently. Given a factorization, you can just multiply and check. So this is basically completely solves the problem of a benchmark, and I just seen this on the ePrint server. I haven't yet read it, but I think just from the abstract, it looks like there is this very recent result that looks to me very interesting by Kalai et al., who basically get showed that you could do this kind of benchmark from any non-local game, assuming some homomorphic quantum resistant crypto system. So you can basically demonstrate advantages. So we have these amazing benchmarks, and maybe if the benchmark problem is solved, then maybe the talk should, there is nothing to talk about. And the reason that we are not yet done is because right now we still don't have these fully scalable, fault-tolerant quantum computers that can run Shor's algorithm, for example. Right, so we still, we want to do this when our quantum device is a noisy quantum device. So we want benchmarks where that we can actually execute on the quantum device that we currently have. And this is the focus of this talk. So there have been basically two general approaches for speedups on these noisy quantum devices. So one approach is been called sometimes quantum supremacy, sometimes it's been called quantum advantage. In this talk, I'm going to call it quantum sampling advantage. So to distinguish it from the other type of advantage experiment I'll talk about. So quantum sampling advantage, generally the idea is that theta describes some ideal noiseless quantum circuit. And we implement it on concrete noisy hardware. So the benchmark is some distance metric between probability distribution, between the probability distribution that the noisy hardware produces, the output that the noisy hardware produces, say, on the all zeros string when the gates are arranged according to theta, and the ideal probability distribution that the noiseless quantum circuit would have produced. So is that clear? So do let me know if there are questions. So this is one type of benchmark, and generally this so here the quantum device is the noisy implementation of the circuit, and generally this benchmark, if you choose the right distance measure right, then it does have statistical efficiency. Generally, it will not be computationally efficient. So generally, it will be because the ideal probability distribution, to evaluate it, we really need to evaluate the ideal quantum circuit. So to classically be able to do it, we need to spend exponential computation time, but at least it's statistically efficient if we choose delta right. And the second approach is a quantum optimization advantage, where theta would be a description of some combinatorial problem, and for example, a constraint satisfaction instance. And the benchmark is just the value. So the output is a distribution over, say, assignments to this problem theta. The device is some implementation on some hardware of a local quantum algorithm, and for example, Eddie's quantum approximate optimization algorithm, and the hope is that we find some instance and some implementation where the value that we get in the benchmark is better than what we could get in a classical algorithm. And this benchmark has disadvantages that it's computationally efficient, because given an assignment, you can figure out what's the value of this assignment. And it's, in fact, even useful. Maybe that depends on exactly what theta is, but generally it's even useful. So obviously it's something that we're very interested in. And so these are two types of results. In this talk, I'm going to show a non-trivial classical algorithm that achieves some non-trivial values of this benchmark for where delta is the cross entropy benchmark. And the second thing is a partial limitation for local quantum algorithms. Showing that there are some limitations to what you could get with very, very local algorithms for a certain constraint satisfaction problem. So I should say,
sorry, Boaz, there's a question in the chat. Maybe I'll let Michal ask the question directly.
yes. Sure.
Michal, do you want to go ahead? Okay, I guess the question says, are there known results that give statistical efficiency here? What about the no-go result by Kleisch et al.?
So I don't know the result by Kleisch, but I mean the XCB is you can evaluate the XCB I think under natural assumptions. You do get statistical efficiency. It is true that and I'll get to it in a few slides, or maybe a few more, but it is true that for some natural choices of the metric delta, you will not have statistical efficiency. So maybe the most natural, like the first delta that you'd think of, like statistical distance or things like that, they would require an exponential number of samples. Yes, L1 distance, like the total variation distance, is an example of a metric where you would need an exponential number of samples, which is why we cannot use it. We need to use other benchmarks. Yes, Vinod.
So Boaz, the factoring thing, can be cast as a sampling advantage in a naive way, right? I mean, the point here is that you need to achieve completeness with a relatively small n. That's the point.
Mm-hmm.
So I can write down Shor's algorithm, right? I can sort of do error correct, like a fault tolerant version of Shor's algorithm. Then that would give me what I want with sampling advantage, right?
Yes.
But the point is that the completeness will be, the n you need for completeness will be tremendous.
I mean, basically the point is that we cannot run it yet, right? We don't have the device right now.
Okay, so yeah, right. So completeness
so you can say
issue.
completeness, yes. Completeness with respect to what we can do right now. So if you want to say factor 2048-bit prime right now, we don't have them. Right. So yeah, and I should say these results, like I should emphasize what these results don't say. So they don't say that these are kind of negative results, but they are very partial negative results on these advantage type of algorithms. So they don't say that the current quantum devices can be approximated, can be simulated. They don't rule out using all XCB in all cases, and they also don't rule out QAOA for all CSPs, or even QAOA for even for MaxCut. They do show, and I think maybe it's better to leave this to the end of the talk, discuss both in the end of the talk and in the panel. You can interpret these things. I think there is both a half empty cup point of view and a half full point of view. So you can say these show some challenges to how you would certify speedups with noisy devices. So some things you have to be very careful on how you choose your benchmark, etc. And they can also look at basically these results give us some things that we need to bypass. They tell us exactly what kind of things we need to bypass if we want to actually bypass these limitations and achieve both sampling advantage and optimization advantage. So this is definitely not a quantum skeptic talk or anything like that. But I think there are interesting subtleties here, which I hope we'll get to discuss. Okay, so if no more questions, I will continue. So I'll start with the results on local quantum algorithms. This is a joint work with Marwaha. So the setting we have is say constraint satisfaction problem. We have a graph or hypergraph. Let's say right now think of a graph, and where each label edge E is labeled with some constraint that takes I should have said an assignment over some alphabet of the vertices of E and maps it into a number between 0 and 1. And for any assignment, the value that the value that the instance theta achieves at x is the average value for over all the edges. Okay, and example, maxcut is a binary alphabet. The constraints are 1 if the assignment on an edge is different for both vertices and 0 otherwise. For example, this is a graph, and say an assignment here is you have these blue edges, and you have these blue vertices. They say get a 0, and the red vertices get a 1, and the edges that are solid, those are the ones that are cut by the cut, and the edges that are dashed are the ones that are not cut by the cut. Okay, so this is, and I think this is actually the maximum cut of this particular graph, although don't don't test me on that. I will not be super surprised if I got it wrong. Okay. So a local algorithm, say a k-local algorithm, is one where it has the following form. So it's a quantum algorithm on some qubits, and we have some way. So basically, we run the quantum algorithm. We start with some initial product state, and we get some distribution which assign a value between, say, 1 to d for every vertex, and then we map it into our alphabet of the constraint satisfaction problem, whatever it is. And we say it's k-local if the output at any particular vertex, it just depends on the initial assignment of things that are in, say, some k neighborhood of this in the graph. So it's one local, for example, if it was one local algorithm, then the blue, the output in this blue vertex that has this arrow on it will only depend on the initial assignment for it and its two neighbors. And similarly, the output for this other vertex will only depend on the initial assignment for it and its two neighbors. And for example, here you would see that because the distance in the graph of these two vertices is more than 2, so they don't have a common neighbor, then their probability distribution of their output will be independent. It doesn't depend on it does depend on the instance theta. It's not independent, but it's independent of any additional, say, randomness. And one example of such an algorithm is the QAOA, say, if you run it for maximum cutoffs, generally for CSPs. And the reason we like local algorithms is that at least heuristically, you can also make this precisely. If your algorithm is local, then it is also noise tolerant. So generally, if your algorithm, each output only depends on a small, say, a small number of gates, then you know, if the probability of each gate to have an error in it is delta, then as long as delta is small enough compared to the number of gates that your output depends on, then you know, most of your output bits will be correct. And in CSPs, generally, if most of your output bits are correct, then you also get a value that is mostly that is close to the value you would have gotten even if you had no noise. So generally, if you have a local algorithm, then the impact of noise is bounded. Well, if you had a very, say, deep algorithm, you know, very deep quantum circuit, then you know, eventually errors will accumulate. So these are very attractive for us in terms of in terms of actually running them on actual hardware that we have. And Eddie and Hao showed that these local algorithms, and there have been other results on also on constant depth circuits, that basically we do not believe there is good computational complexity reasons to believe that you could not simulate these algorithms. So you could not classically produce the same probability distribution that they produce. And under maybe stronger assumptions, you could not even approximate it in statistical distance. But it doesn't necessarily say that you could not. So even with locality 1, you could not classically fully simulate this algorithm. but it doesn't necessarily say that you could not match its performance without simulating it. And this is basically a question we don't know the answer to. So the following is open, and I think it's one of the reasons I want.
Boaz, I think it's a little confusing. So what are you saying here? That there's no classical algorithm that can sample from the same distribution? So
yes.
Even in a noisy case, or what's this result?
So I think Eddie's result, I think it's in the non-noisy case, if I remember correctly. But I think you with stronger assumptions, you could believe that it's also true in the noisy case. I don't know if Eddie wants to chime in, but the actual probability distribution. So there is two things, right? So suppose you're thinking of maximum cut, right? So you can and suppose you have a particular instance theta, and the QAOA outputs some probability distribution over cuts with expected value 95%. Okay, so there are two separate questions. One, could you output the same probability distribution? And the second is, could you output a different probability distribution that also has a similar expectation, that also has expectation 95%? And the first, obviously it's a much more challenging task for a classical algorithm to do the first. And the first, we have some evidence that it might be hard. And the second, we don't know. Mm-hmm. And this is basically, I think, like a very interesting question. One of the reasons I wanted to give this talk is maybe to popularize this question, which is this question whether, and this is I should also say, this is a question in an asymptotic setting. And in real life, nothing is asymptotic. And, in real life, the number of locality is not necessarily constant, and the number of qubits is not approaching infinity. But I think it's a very nice theoretical question, which we don't know the answer to. And the question is the following: could it be the case that for every constant local algorithm, you have in every epsilon larger than 0, you have a poly n classical C, where the poly in the exponent of this poly might depend on the constant epsilon and the constant locality, and you think of n as going to infinity. And so for every CSP, and let's say the CSP is bounded degree, so constant locality makes sense. So for every particular instance, so for every point, so for every particular instance, the classical algorithm gets a value that is as good, at most epsilon worse than the quantum value. So I find the fact that we don't know the answer to this question, or even very good, empirical, very good conjectural answers to it, I find it very, fascinating, and I think this is a question we want to know the answer to. So because if we know we know that basically if you had like fault tolerant algorithms that are not local, then definitely the answer to this is no, because we can encode factoring as a SAT instance, and use the PCP theorem, so there will be even like SAT instance where it's 1 versus 7/8. So we know that the answer to this, if you were talking about general quantum algorithm, is no, but we don't know what the answer is when you're talking about local quantum algorithm. And the question, there is a question now I see in the chat, something about special classes of graphs. So generally, we don't know how to rule this out. We don't know that this, as far as we know, this might be true for all possible graphs and for all possible CSPs. In some sense, we will see that this is true for in this talk for high graph max cut and one locality, which is a restriction on top of restriction on top of restriction. So. But for an initial result, I think, this is just starting to explore this.
Boaz, are you assuming a geometry for the locality? Is this like on a grid or?
Yeah, so I'm assuming any graph, but let's say constant degree graph.
Okay, but so these light cones could be like like exponential in depth of the quantum circuit?
Yes, but right now we are thinking of it constant, and the n goes to infinity. So yeah, so generally, I think this is yeah. Generally, you could ask yeah, like yeah, you could ask this question for particular graphs and for particular. I mean, I think this is the first question you want to answer. If, for example, the answer to this question is yes, then you could ask how does you know, the complexity of this classical city depends on this locality, and they could still be very meaningful speedups if, for example, it turns out that you know, the classical C needs to run in time that is exponential in the light cone or something like that.
Okay. Yeah, because like the graph is expanding, or you know, has interesting properties. It changes dramatically, I feel.
Yeah. I mean, yeah, and again, like, and I think what you know, and I probably will talk about this in the panel, but I think a good point, which I'm sure Eddie will make if I won't, wouldn't make it myself, is that in real life, the number of qubit is not going to infinity, and so it's not. So the locality is not necessarily the right way to think about the locality, is maybe not necessarily as a constant that is independent of the number of bits. But I think this is for a first theory question. I think it's a good question to know the answer to. At least I want to know the answer to it. So our result, basically, we just looked at one local algorithm, and we looked at all maximum cut instances of a large graph, and say large here would be larger than 3 or 5. I think I think we need no 5 cycles, and we showed that the value that you get in these graphs, that the quantum algorithm is less than half plus 0.71 over square root d. Now this looks like an arbitrary number, but the nice thing is that it is really actually bounded. In this case, you're getting worse than what the classical algorithm will get. So at least in the high degree, high graph case, you can show that there is a polynomial time classical. I mean, I cannot show it, but El Alawi, Montanari, and Selkesh did show that there is a polynomial time classical algorithm that gets this value, that achieves this higher value. And the other reason why I like this result is that it's a different type of technique than what previous limitations for local algorithms, in the following sense, that typically the way people have shown, like that max cut is hard to approximate for some local algorithms, is you basically show that maybe a local algorithm cannot distinguish between a random deregular graph and a random deregular bipartite graph, where in the bipartite graph, in the random deregular bipartite graph, the value is 1, and in a random deregular graph, the value is close to half. But how close is it to half? It's actually close. It's actually this close, like 0.76 over square root d close. So you cannot use this indistinguishability type of result to show limitations to show this kind of result. Because basically, in this instance, this is the kind of domination that we're interested in the sense that for this particular instance, there actually does exist a graph, a cut with a value at least half plus 0.76 over square root d, but the quantum algorithm doesn't find it. And the classical algorithm, yes, it's local, but it's not one local. The classical algorithm, I believe it's local. I don't think it's written in the paper, but basically, it's some approximate message passing algorithm, which I think can be truncated to be local, but like the locality will be terrible. Like and it's definitely like the classical algorithm is not like the quantum algorithm. So I should say we have some ongoing work where we are looking at relaxing the low graph, the high graph condition. So I think that would not be a deal breaker. But right now our results, the technique which I'll show you that breaks when we look at two locality, and also is right now very, you know, when you look at more CSPs that are more complicated than MaxCut, in particular ones that are on hypergraphs and not graphs. And yes, and Kunal, my co-author, wrote in the chat exactly the right answer regarding locality. Thank you, Kunal. Yes, and co-authors in the audience, please feel free to also correct me in the chat, and or I add the information at any point. Okay, so because the proof is actually simple, I wanted to show you at least a very quick overview of this proof. So basically our focus is we're going to show the following lemma. So 0.71 is basically square root 2 over 2. So the lemma follows from the following, the proof follows from the following lemma. Suppose you have a probability distribution with mean 0 and over the graph, such that every two variables that corresponds to vertices of distance more than 2 are independent. Then if you take a random edge in the graph, then and this is a deregular graph, then the expectation of the correlation between xi and xj would be at most square root 2 over d. And the lemma just follows, like if you have the lemma, then the result above just follows directly. Just you know, you just change from 0, 1 to plus minus 1, and you just divide by 2, so square root 2 becomes 0.71. Okay, so this is just the this lemma. And now let's look at the proof. So let's consider the normalized adjacency matrix of the graph. And we want to bound the expectation of xi, xj, where I is a random edge, and expectation also for the x's. We want to bound this squared by 2 over d. So let's see how we get there. So we start by, you know, Cauchy-Schwarz, take the expectation of x and take the expectation of over the edge inside. And then by some manipulations that I'm going to skip, you can show that you can bound this by basically taking x transpose a squared x. So basically this, instead of taking the correlation between, say, xi, xj for a random xi, xj squared for a random pair, you'll take basically, you take a path of length 2, and you take the correlation between two random points of this path. And let's call this quantity mu. So we got that the quantity we're trying to bound squared is bounded by mu. Now we basically can, you know, a squared, it's a PSD matrix, and you get this, and its eigenvalues are, you know, some the lambda i's. Then you take a to the 4, it's like lambda I to the 4. So this is lambda I squared, this is lambda I to the 4. So again, you do some Cauchy-Schwarz, you can bound this expectation of x transpose ax divided by v by expectation of x transpose a to the 4x divided by v. This is, you can do it pointwise for every x. So in particular, it's true with expectation over x. So this is basically, you take the two endpoints of a length 4 path. Now what we do, we look at is the following. Now we want to use this assumption that we have. So if you look at the length 4 path, then the only way there would be a correlation between the orange point and the red point is if this 3-point path from the green point to the red point was happened to be of length 1. So this is a length 3 path, So it can be either, it can be of either length 3 or everything is different, or it can, one edge could kind of repeat, and then it will become a distance, the two endpoints will be of distance 1. And if the two endpoints are of distance 1, then we basically get the same term mu that we got before. So, so basically we get here the probability that the length 3 path, the two endpoints are of distance 1, times mu, which is the correlation between two distance 2 points. And now there are two options for length 3 paths to collapse to become a distance 1. One is that you take two edges and then a back edge, and the other is that you take the first edge, then go back and then go somewhere else, because this is a graph of high girth. Those are the only ways you can happen. Each one of them contributes to us like 1 over d. So you basically get that mu is at most square root of 2 over d times mu. And now we do this algebraic manipulation and we just get the result. Okay, so this was short and simple, but it is different, a different proof approach than the ones that people have used for limitations of local quantum algorithms before. Okay, so now we can briefly, if there was too much algebraic manipulations, then we're done with that. And this was basically my summary of that part of the result. So now let me talk about the other part, which is these non-trivial classical algorithms for sampling advantage. So now, if we ask this question about sampling advantage, then we need some kind of a benchmark. And maybe the first benchmark that quantum scientists would look at is what we want is that the quantum device has good fidelity with the true state, right? So the true noiseless quantum circuit would produce a quantum state phi, and we can define the fidelity of the noisy quantum circuit as the fidelity with the ideal quantum state. So that I think would be maybe the most natural definition from the point of view of a quantum scientist, but this definition doesn't make sense for a classical algorithm, right? It's not a benchmark in a sense that there isn't, it's a function of a quantum state, and a classical algorithm doesn't produce a quantum state. So this is just basically, you cannot punish the classical algorithm for not producing a quantum state. That would be, that has to be like against the Geneva Convention or something like that. So, so this is not a good benchmark, but basically the same benchmark, we can define a version of it, which is the Bhattacharya distance, which would be, would correspond to, would be the generalization of these two probability distribution or the restriction of these two probability distributions. And you can have other versions like total variation, Kell divergence. The problem is all these natural probability distance measures, generally they require exponential in n sample complexity. In almost all of these cases, you can have this probability distribution that is, say, very, very far from the uniform distribution, but it would take you many samples to distinguish between that and the uniform distribution. So we need some kind of more exotic distance measures, and the one that people have settled on, and maybe there are others that might be better, is this linear cross entropy benchmark. And so this is the one way to think, it's just for probability distribution Y, you just get the 2 to the n times the probability. So you sample from Y and you look at the probability of the output that you would have gotten, and you subtract 1. So in particular, if say Y is the completely uniform distribution, so if Y is a completely uniform distribution, the cross entropy would be 0. If Y is kind of a random, if theta is a random circuit, then the ideal the ideal probability distribution will get a linear cross entropy benchmark of 1, because generally this will be a Porter-Thomas distribution, and you can show that this would be the expected of you get expected Gaussian. The expected Gaussian squared is 1, and now you get the expected Gaussian to the 4 is 3. 3 minus 1. Yeah, I think it comes out to be 1. Maybe it's 2, but but a constant. And if C is uncorrelated with theta, then basically a typical Y will give 2 to the minus n, and then we will get a cross entropy benchmark of 0. So generally, in this cross entropy benchmark, if it's bounded away from 0, we think of it as non-trivially correlated with the ideal distribution, and if it is negligible or goes to 0, then we think of it as uncorrelated. So it's a measure of correlation. And the nice thing about it is that you only need to show that it's bounded away from 0. You know, if it's epsilon, then you need poly n samples. So that's even if you need you know, exponential in n time. So it is statistically efficient. It is not computationally efficient, but you know, at least it's something. So the way we do, here is a cartoon of how we do sampling advantage experiments when we are in a situation like that. Then basically we have whatever the benchmark value that the noiseless circuit would have gotten. And then we have this experiment. And typically what happens in this experiment, we can run it. And at some point, and at some point we have to extrapolate, because at some point we cannot compute the benchmark, but hopefully the curve looks clean and nice enough that we can extrapolate and get a good sense of what the benchmark would be if we had been able to compute it. And then, you know, for it to be an advantage, it should be a higher benchmark than what we know how to achieve classically. And ideally, I mean, it should also be, for it to be a proper benchmark, it should be under some conjectures better than what the best classical algorithm within certain resource bounds. So, you know, with actual experiments, you do this kind of thing, and then you run the experiments in a range above of what you can actually classically verify, but you have evidence from the lower size experiments why you think the benchmark will be what it is. And Google has done it, and also USTC, and then and they generally have gotten, you know, for say 53 qubits, 56 qubits, 60 qubits, have gotten values of the benchmark that is maybe not very high, but at least are bounded away from 0. But at least for the Google case, the Pan and Zhang have managed to simulate and get an even better value for the benchmark with a classical computer. So I'm not sure, there is some comment on the chat which I'm not sure if I understand, so I'm not sure if it's a question or but people can feel free to clarify. So what we have done is used a single GPU and in 1 second and gotten worse results. So we have so while Pan and Zhang have benchmarks that are larger than say Google and Google, we have given benchmarks that are lower than Google or USTC, but are in the ballpark. They are also non-trivial, and they're much less computationally expensive. And maybe also interesting is that at least in some, there are many different ways in which you could extend their the architecture to 70 qubits or larger number of qubits. Yes, so there is a comment that it does not sampling the right distribution. Yes, I mean, it is, we are talking here about a benchmark, and the benchmark is the XEB benchmark. It is not close to the probability distribution with, yes, so within some other notions of distance. And yeah, we can, but this is a very a very good point, which we'll, I'm sure we'll also talk about in the panel. So right now we are fixing a particular benchmark, and PZ and us, definitely not us, and definitely not PZ, are not simulating. In fact, I'll soon say exactly how we are not simulating the quantum circuit. Yeah, but you need to, yes, and there is a good question if you need to find the high probability bit string, or you can define that the benchmark is to find many of them, but we can discuss this more in the panel. So, so basically, one of the things that's interesting is that at least in some measures, you might think that usually the way you think about in quantum supremacy, and maybe I'll put the graph on. So usually the way you think about in this type of supremacy experiments, or in general, when you have one more advanced technology against one less advanced technology, is that you just turn the dial up and it's game over. Like, you know, once computers beat once computers you know, beat humans at chess, you needed to wait maybe one more year, you just bigger computers, and it's kind of completely all over. So you might think that, I mean, and this still could be the case also in quantum, that basically we are now at the edge of supremacy and the classical algorithms could give a good fight, but you simply scale it up and it's all over. And what these results show is that scaling up doesn't just mean increasing the qubits. That is not enough. You need to also improve the fidelity or decrease the noise. So, so if you simply increase the number of qubits, it might depend on exactly the geometry of how you do it, but generally you simply increase the number of qubits, you could actually be hurting the noisy quantum circuit more than you hurt the classical algorithm, at least for our algorithm. So, our estimation, which is estimation that we didn't run unlike this, is that basically at 70 qubits for natural extension of the Sycamore architecture, our 70 qubits our algorithm and Google will meet. So yes, and I'm not sure if there is a question in the chat, but maybe, I mean, we can also like keep these things to the panel if there is more general question.
You should go on because you're running out, you know.
Yes.
Let's save questions to the panel.
So the intuition behind these things, and let me maybe I'll go a little bit, is that indeed, in some sense, it's exactly what Sergey said. Indeed, if you're just trying to maximize the coarse entropy benchmark, then you can cheat a lot. And maybe Pan and Zhang cheat in one way and we cheat in another way, but generally, yeah, you can, the fidelity measure or say other standard measures of probability distribution can be, if you're in an adversarial setting, and when you are the classical algorithm, you can specifically be in the adversarial setting, then you can actually manage to have a very poor simulation, so very poor in terms of say fidelity simulation of your of the underlying circuit, but one that is actually pretty good in terms of XCB. And we show that basically, for example, if you look at a noisy circuit, the ratio between XCB and fidelity, our algorithm in some sense specifically tries to drive this ratio to very large values, so it will have very poor fidelity, but very good XCB, or at least pretty decent XCB. So and one intuition for this would be the following, and again I'll do it quickly because I think I'm running out of time. So one intuition, maybe I'll just skip the calculation.
So sorry, Boaz.
Yes.
Maybe since this is a critical part of it, you could take a few extra minutes. But
okay.
I didn't actually follow the last slide at all, so it seems like it's an important slide. So first of all, what's the blue and the red dot? What does it mean?
Okay, so here we measure we divide. So we take our algorithm and we take a noisy circuit, say this also depends on the gate, but let's say.
Sorry, this is all quantum now. You don't have a
quantum.
classical, nothing classical in sight.
Now it's not classical because our algorithm basically essentially designs a quantum circuit that is a different quantum circuit, a different noisy quantum circuit, and then just simulates it fully. So this is just quantum, and this basically we look at the ratio between the XCB measure and the fidelity.
Mm-hmm.
So you can see that if you have, say, a low noise noisy quantum algorithm, you actually the ratio is bounded. So basically XCB is very good proxy for the fidelity.
Mm-hmm.
And if it's a little bit more noisy, it's a little bit worse, but still decent. But what we show is that you can actually break apart the connection between the two. So you can cheat in the sense of getting a good XCB value, while even if your fidelity is very poor. Okay,
Mm-hmm.
so we are deliberately breaking, and there's some intuition why they are different is in this slide. So the XCB is right. This is the measure of XCB between two probability distribution. Now let's think of fidelity is basically corresponds. You have two probability distribution. You can think it's the dot product of the corresponding unit vectors, right? So given a probability distribution, there is a unit vector which is the square root of probabilities. So the fidelity or Bhattacharya constant, if you're thinking of it as classical probability distribution, is just the dot product of these two unit vectors. So now, right now, maybe this seems kind of the same, like it's not maybe not clear what's the difference, but here is maybe an example that demonstrates it. So suppose you have like system with two parts, and you have two independent probability distribution of these two parts. So now suppose that the XCB of one part is chi1 and the XCB of another part is chi2, then the XCB of the joint system, you can do the calculation, right? To get the probability of y equals x, you add 1 to the XCB and you divide by 2 to the n over 2 if it's a system of n over 2 bits. So you just do the calculation and you see that the dominant term, assuming these two things are pretty close to 0, the dominant term is chi1 plus chi2. So the XCB of two independent systems is the sum of the XCBs. On the other hand, if you look at the fidelity, it's basically like the dot product of the two tensor things, which is the product of the fidelities. So the XCB adds while the fidelity multiplies. So you can see this is quite different behavior. In particular, if say you injected some noise into the circuit that broke it into two parts, and you managed to get a decent XCB in non-trivial XCB in each part, then this adds up. Well, on the other hand, if you were to do this with fidelity, you kind of lose because you take the product of fidelities. So that's basically the intuition why if you have a noisy circuit and there is the same amount of noise, but it's distributed differently, this could have a dramatically different effect on the XCB value versus the fidelity. Now, if you have very few errors and they are in random location, then generally this will not be the case. They will have similar effect on XCB and fidelity. But if you put this noise in the right locations, then this can make a very different effect. So basically, and this is both due to additivity and also to some cancellations, which behave differently in XCB and fidelity. So basically, what our algorithm does is we take a noisy quantum circuit, but we choose the location and the type of the errors so that they are, on one hand, they're chosen to make our life easiest when we're trying to simulate the circuit. So they're trying to break it apart to smaller systems that we can simulate. And they're trying to maximize the XCB, so have like the smallest impact on the XCB. So trying to make sure that the impact on XCB is small, but the impact on computation cost is large. And then you also do some post-processing to amplify this XCB. And yes, and this is basically the same graph. You can see, in one-dimensional circuit or two-dimensional circuit, the algorithm does very quickly, very well. In the Sycamore thing, we are worse than Google again in this benchmark, but you can see that in some sense the scaling is actually better. And in particular, you can show that for several architectures, you can get XCB that only descends exponentially with the depth rather than the size of, and that is contrary for this particular architecture. Aronson and Gunn have kind of a generic conjecture that no classical algorithm could get. It will need to. It will get only XCB that is exponential in this exponential in the size, inverse exponential in the size, and we can get inverse exponential in the depth. And let me, yes, since I'm out of time, then let me finish with some conclusions, and then we can, I'm sure there's going to be a lot of discussion. So you can have you can look at the glass half empty and the glass half full of these type of results. So in general, for this is the lesson we learned from cryptography, that whenever you have attacks or spoofs, they only get better, they never get worse, right? So classical algorithms will only get better if you achieve, say, a certain value in the benchmark with this classical algorithm. Next year, someone probably will find a better classical algorithm. So in that sense, that's maybe a negative result for the quantum optimist point of view. But the other part is that quantum hardware gets better, and also maybe techniques for error corrections. And as time gets by, we get closer and closer to the full fault tolerance. And once we do that, then there are like these qualitatively different benchmarks that where the classical algorithms don't seem to even stand a chance. And another negative result is that while our results right now are just for large graph or maximum cut, I think there is some indication that maybe some of these ideas could extend beyond it. But I should say that some current hardware platforms like Lookins do have some non-local operations for, say, independent sets. So the Hamiltonian is not purely local. And this approach might extend beyond high graph or max, but it completely fails if once you get to the point where the light cone is all the graph, where basically every output depends on all of the graph. And right now, that's already the case in, say, the Sycamore circuit, but the problem is that the Sycamore, if you think of it for optimization for CSPs, then this is not great because it has, every output is like 98% noisy and maybe 2% not noisy, and we would like it to be the other way around. But eventually with lower, and also the instances maybe are kind of small, but in principle, this, once you get noise to be low enough so that you can afford to have the light cone be everything, then all of our negative results completely fail, the approach that we use. And also it doesn't rule out polynomial speedup, and we have a recent paper with an implementation where we seem to observe that some empirical evidence for superlinear speedup. And with sampling, maybe the negative result, the negative view is that you cannot just simply increase the number of qubits, but every year people improve not just the number of qubits, but also the noise, and the noise really makes a huge difference. So we've seen it in some of these graphs, like if you reduce the noise, even if you don't reduce it all the way to fault tolerance, you could already reduce it so that the classical competition has a much harder yes, and also, and this maybe is related to Sergei's question. These are not full simulation. This doesn't simulate the probability distribution. It just achieves the cross entropy benchmark, and you could potentially find some other benchmark. I would just say that it's good to have a benchmark that is, specified, written down, and one that we can evaluate using a polynomial number of samples. So, if there are alternative benchmark, that would be very interesting, especially if we could find an efficiently computable benchmark for this type of random circuit experiments, that would be, I think, wonderful. But we don't know anything like that right now. And with that, let me finish and answer questions of the panel. Let Umesh decide on how we proceed.
Okay, so thanks a lot, Boaz. That's great. So maybe in view of the time, we can move on to the panel and then fold the questions into that. Perhaps as the panel, panelists being set up, if there are any questions.